So here in this particular video, we have a box of 200 kilograms, and it is experiencing an applied force F here with the magnitude of 35.8 Newton as stated in the wording, and then theta here is 42.1 degrees, and it says here there is a kinetic frictional force that acts against the direction of motion, aka opposite of the velocity. Okay, so in this case, it's moving to the right of the screen, and then it is rough, so therefore there must be a kinetic frictional force that acts against it. And down here we have the coefficient of kinetic friction, which is not given to us. So if you need to, pause the video, write it down. Other than that, let's knock it out. All right, let's do part A and B here. Part A asks you to find the magnitude of the kinetic frictional force. So here, F of K is directed leftward because the box is being pulled to the right. Okay, so F of K for this particular problem is going to be negative because it is pointing leftward. All right. So in order to find part A, you have to identify all your force or force component in the horizontal direction. In this particular diagram, the force that's being applied is a diagonal, aka is pulling to the right and upward. So therefore, it must have a horizontal component. So the dashed red line that just came up, that is my F of X, aka my horizontal component of the applied force. Okay. Now that you have all the forces identified in the horizontal direction, there's no additional forces here. It's simply F of K pointing left and F of X pointing to the right. So therefore, to find F of K, we focus our attention in the horizontal direction because F of K is in the X direction. So I'm just going to set up Newton's second law, except I'm going to focus my attention here in the horizontal direction. Hence, I put sigma F, except it's sigma Fx equals MAX. From there, I can just focus my attention and really just introduce the forces that are along the x-axis. In this case, I have Fk and F of X. Okay. The way I do it is that I will always write my positive vector or vector components first. So in this case, between Fx and F of K, F of X pointing to the right. So I will write that first in my work, and then I will subtract it from everything that acts against it. In this case, it'll be F of K. All right. So in this case, the second line that comes up here is F of X minus F of K equals MAX. Again, I will write all my positive force vector or vector components first, and then I will subtract it from everything that is acting against it. So I think this is an easy strategy to do. This way you don't get mixed up with your signs, okay? From here, you do have to read it a little carefully though. For this particular problem, it does say constant velocity. Because it says constant velocity right away, it suggests that the acceleration in the horizontal direction is 0. Okay, when an object moves at a constant rate, it is not speeding up nor slowing down, so AX is 0. So I did a quick substitution there. AX is 0. Mass times 0 is just 0. But here on the left side, I have F of X minus F of K. But what I do know though is that F of X can be substituted for F cosine theta because the horizontal component here is the hypotenuse times cosine because it is the adjacent leg. Okay, so just a quick geometry there. Therefore, I can now set the whole function equal to 0. From there, I can just solve for F of K because essentially part A is asking us to solve for F of K. So on this side, I have F cosine theta minus F of K, which is equal to 0 because mass times 0 is just 0. And then I'm going to move this negative Fk to the right side of the function to isolate for it, which changes the sign. So it went from negative to positive. So here I have a statement that's true. I have F of K is F cosine theta. And then I know what my F is. I know what my angle is because those two values are given to us in the statement. Here the applied force is 35.8 newtons. And then the angle is 42.1 degrees. So it just calculated work time. If you do this properly, the answer for F of K is 26.56. Why it is directed leftward, the question in part A asks you to find the magnitude. So you notice here my answer is just the scalar value, or just the scalar of the force, okay? So the answer is just 26.56 Newton. I don't need to include directions. All right, well, let's go ahead and do part B. Part B asks you to find the magnitude of the contact force exerted by the floor onto the box. So anytime there is a contact here along the surface, there is a normal force that's pushing upward onto the box by the floor. So I'm going to go ahead and identify all my forces here in the vertical direction because F of n is perpendicular to the surface, and the surface in this particular problem is the horizontal direction, aka X, therefore perpendicular to be the Y direction. So therefore F of n is pointing upward. Okay, and I label that vector f of n. Here things are not drawn to scale, by the way, so it's just to help you visualize what these forces need to look like. So that's f of n. The other vector that I do have is that I do know because there is a mass of 200 kilogram that's sitting on the surface, there must be a weight that's pulling it down or keeping on the surface. Therefore, this vector here is what I would call my weight, or aka my force due to gravity, and the force due to gravity is by definition mass times gravity at the surface of the planet. Okay, so there, and then last but not least, though, I almost forgot, because F here is a diagonal, you have to have a horizontal component and a vertical component. In this case, the vertical component is pointing upward because this applied force is to the right and up. Okay, so it's important that you draw these directions carefully, otherwise you can mess up with your net force. All right, so Fy is pointing upward. So here I would just do the same process except for the y direction. I'm going to apply Newton's second law again. So the only difference here is that instead of saying sigma fx, this is sigma fy now, which is may. Okay, and I'll do the same thing I did with the x direction. I like to add up all my forces that are positive first, or pointing upward in this case. So I notice here there are two forces pointing upward, Fn and Fy. So I take care of all my positives and then I'll take care of all my negatives. Okay, so in this case I notice that there are two vectors pointing upward and there's only one pointing downward. So in my work I will write Fn because it's positive. I will also add it to Fy because that's also positive. And then I'll subtract it from anything that's negative. In this case, there's only one vector that's in the downward direction, which is the weight of the box. Okay, so that's f of g. And here ay is equal to 0 because for these types of problems, the box is to remain on the surface. It is not to fly up or, just disappear. All right, so ay is going to equal to 0 because the box itself is not permitted to accelerate upward in this perspective. All right, therefore, to isolate for Fn, I would just move f of g to the right side, which makes it positive now, and then f of y, this is a positive y, so it now becomes negative f of y. Okay, therefore, all we have to do is really just plug and check. F of g is by definition mass times gravity. We're going to subtract fy, just got substituted for f sine theta. So back to this diagram here, just in case your geometry is lagging a little bit. This is your angle here. So therefore, f of y is your opposite. Opposite in geometry is your sine. So by definition, sine of theta equals opposite, which is this, over hypotenuse, which is f. So if you manipulate and solve for f of y, you should get f sine theta. Okay. And now we just plug and chug. Here, mass is 200 kilogram. G here is 9.8. I'm plugging in 9.8 here because in this statement up here, that I'm circling back and forth. Okay. I have already stated that the force of gravity is negative. It's negative because the acceleration due to gravity is negative. So I've already taken care of the negative sign in the negative 9.8. So when I get to my work here, I plug in a 9.8, a positive 9.8, because I have already taken care of the negative 9.8 earlier in my work. So it's important that you do that and you notice and you keep track of when you've taken care of the negative sign. So here, it's positive 200 kilograms. A positive 9.8, and then subtract it from f, which is 35.8 sine. The angle here is 42.1. So if we put it on a calculator, you should get a difference of 1936. Okay, 1,936 newtons. All right, so that is your answer for part B. So the normal force is 1936 Newton, and that's for magnitude, so I don't need to say upward or positive or anything like that. All right, let's do C and D. Part C asks you to calculate the coefficient of kinetic friction. Well, part C is pretty straightforward if you know the function for the coefficient of kinetic friction. The coefficient of kinetic friction is simply the ratio between f of k and f of n. Okay, so we already know these values. For f of k, we already know from our previous calculation that it is 26.56 Newton. We just found f of n in part B, which is 1,936 Newton. So you notice here the units will cancel out. Okay, so really you're left with just 0.0137 Newton. And so that is our coefficient of kinetic friction. This value tells you how rough the surfaces between two objects are. Okay. Therefore, this one, it's important to note that there is no unit. Okay, so the answer when you're asked to calculate for the coefficient kinetic friction should have no unit because it already cancels out. And then it should have no direction because the roughness of something has no direction. It's a scalar quantity. All right, other than that, that is the answer to part C. So it's important to keep track of these things. Sometimes folks who are new might be tempted to put a negative coefficient, or they might put a unit. All right, let's do part D. Part D asks us to calculate the acceleration of the block if the angle is reduced to 18 degrees. Well, I just modify this diagram for you. So here we go. It says 18 degrees, so I want to draw the applied force just slightly slower at a lower angle. So that is still my F. My angle here is 18 degrees. So therefore, to find the acceleration, I would need to do the same process as earlier, except I'm just going to use a new angle here. I'm going to apply Newton's second law for the horizontal direction. So sigma fx equals max. All I have to do is find my components again. So therefore, f of x here. Okay. So again, I do my work where I'll write the positive force first, and then I'll write all the negatives after. So here, f of x still is pointing to the right, just because you lower the angle doesn't change the applied force for this problem. So fx minus f of k equals max. And then I can just break up f of x again, equal to f cosine theta. And then f of k is mu k f of n. So watch where I'm circling. This is the ratio in order to find mu k. So therefore, to find f of k, you would just multiply both sides by f of n. So really it's mu k times fn is equal to f of k. So a quick algebra manipulation there. So that's where this function comes from. So f of k is simply mu k times f of n. And then I highlight f of n here because this is usually where kids will make false assumptions too. F of n is going to change based on the types of problem given to you. Okay, so it's allowed to fluctuate. So it's not a stagnant value. All right. You notice here ax is not 0 because now that I'm changing the angle of the applied force, I'm modifying fx, I'm also modifying fy. Lowering the angle increases f of x because cosine increases as the theta decreases. All right. So therefore, I can just now plug in all these values. Okay. However, you notice here I know what f is, I know what the angle is, I know what mu k is. Mu k we found previously, which is 0.0137. But what I don't know is that I don't know f of n. Okay, I do not know f of n, so I have to set up my information in the y direction. But from our earlier work, we know that f of n for this problem is f of g minus f of y. Okay. Now all we have to do is plug it in. Fg is just mg minus fy, and fy here is just f sine theta again. I left the units out here just to save some space on my screen. Mass is 200. Gravity, again, I'm plugging in a positive 9.8, not negative because I've already accounted for the negative sign using my work. All right, minus 35.8 because that's the applied force, and then sine here of 18 degrees because that is the new angle. So if you do this, you'll get an f of n of 1,949 newtons. Well, now that I know f of n, I can just substitute it back in here. This is the only thing that I was missing, okay? I know f, I know theta, I know mu k, I know the mass was given. I'm trying to find a, and the only thing I was missing is f of n. So all you have to do is set up the Newton's second law in the vertical direction the same way as part B, and then find the new f of n by using the new angle. All right. Other than that, I just carry this work down. Watch my cursor. So this statement here, f cosine theta minus mu k fn equals max, I just carry that down. For f, I plug in 35.8 cosine of 18 minus mu k is right here, 0.0137. I substitute that in. I use the new f of n for this one because changing the angle changes f of n. The 1949 newtons. And then over here, this is 200 kilograms because the mass is 200 kilograms. So if you simplify all this on your calculator and then divide both sides by 200, so everything on the left side, if you reduce it, it gives you 7.3. But in order to solve for ax, divide both sides by 200 kilograms. So I did all that in one step just to save some space on the screen. So 7.3 divided by 200 will give you a value of about 0.0365 meters per second square. Okay, and the answer here should be positive, or you should say 0.365 meters per second square to the right. Okay, so make sure to include the direction because it did not use the phrase magnitude. All right, other than that, I hope that helps in terms of just showing you how to manipulate these functions really quick. All right, stay nerdy.